Okay, let's get started. Today we are going to review how to samples from a distribution. Specifically, we are going to discuss Markov chain Monte Carlo methods, which is probably the most popular sampling methods in to represent a distribution. The outline is as follows. We first will give you an overview of sampling methods, and subsequently we are going to discuss three popular methods: rejection sampling, importance sampling, and MCMC sampling. So here is a motivation of the sampling methods. How do you represent a distribution? There are two ways. The first one is to use a closed form representation. For example, if we know that X is drawn from a Gaussian distribution parameterized by mu is the mean, and sigma square is the variance, we can write the density function as Px equals to 1 over 2 pi sigma square exp right? This is a function which has a closed form that you can manipulate with. Many distributions like Dirichlet distribution, multinomial distribution, Bernoulli, beta, and gamma, all of these distributions can be write out with a closed form formula. However, in many cases, the distribution can be quite messy and complicated. For example, what if we have a distribution like this? Can you find an equation to give the density of this distribution? It's very hard, right? So this comes to the second method to represent this distribution, which is called sample-based representation. The basic idea is, instead of find out a closed form equation of this distribution, we draw samples from it. Because the density here is large, so there are many samples here and many samples here. And the density in this region is low, so the samples is the number of samples is small. So if we can find a way to draw many samples from this distribution, we can use the samples to describe the characteristic of this distribution. Let's say an example. Suppose I want to compute the suppose X is drawn from a certain distribution, and I want to compute the expectation of X. If Px has closed form, for example, in this Gaussian case, you can write down an equation of Px. And to compute the expectation of X, you can plug in this equation into the definition of the expectation and do the integration to get this. However, if Px does not have closed form, like this distribution, like this very wiggly and messy for this distribution, it's impossible to find an equation like this. So instead, what do? We draw samples from n samples from this distribution Px. N can be 1. So given these examples, how do we compute the expectation? The expectation can be approximated by the sample mean, right? Xi. This is the sample mean. You simply sum them up and divide by the number n. you can use the sample mean to approximate the true expectation. So that's why if we have many samples of our distribution, we can pretty much represent this distribution. Okay. For example, in EM algorithm, in Gaussian mixture model, remember the lower bound is taking over expectation of the variable, right? So in many cases, we want to compute the expectation of a distribution is arguably the most important characteristic of a distribution. And in a lot of cases, you simply want to use a single scalar to describe the distribution. And this is one example. You can also compute the variance, for example, variance of x, and also the posterior of x given some other data. And also, if the samples are drawn from a joint distribution pxy, you can use the samples to compute the marginal probability of px. You can do many things. Use the samples. Okay. So this is the motivation of the sampling methods. Let's repeat again. For many distributions which are complicated, it's impossible to find a closed form equation to describe this distribution. So we draw samples from this distribution and use the samples to compute the quantities we are interested in. That's basically the idea of the motivation of sampling methods. Any questions about the motivation? Okay, now we understand why this method is important. The next question is, how do we get samples from a distribution? Today, I'm going to introduce three methods. The first one is rejection sampling. Rejection sampling, the procedure is like this. We have a distribution x, which can be written in this way. Potential function over the partition function. You see this in Markov random field, right? The pi prime x is very easy to compute because it is a function, potential function you defined to characterize the probability of x. However, to make this pi x be a valid density, you have to divide the potential function by a partition function. This partition function is a normalizer to ensure the integration of pi x is 1. So given this distribution, how do we get samples from this distribution? So the idea is we are going to use a simpler distribution Qx. This in theory in principle can be any distribution. Usually we choose one which is easy to get samples from. For example, Qx can be a Gaussian, can be a multinomial, can be a Dirichlet, so on and so forth. So given this Qx, let's say it is a Gaussian, for example. We can easily draw samples from a Gaussian distribution. There are many tools to use. For example, in MATLAB, you can use rand_n to easily get samples from a Gaussian distribution. So given Qx, we are going to sample sample samples from Qx. Let's say Q star. After this is the first step. Given a simpler distribution Qx, firstly, I'm going to draw samples from Qx. The next step is to decide whether I'm going to accept this sample or not. Accept means if I accept X star, I believe X star is a sample from the target distribution tags I am interested in. If X star is not accepted, then I thought it is not a valid sample from PAX. So in the second step, we are going to use a probability to decide whether to accept X star or not. And the probability is defined as pi prime x over k Qx should be X star. And the Qx here is the simpler distribution you used. And the pi prime X star is a normalized potential function. And the k is a constant, a very large constant to ensure k Qx star is always bigger than pi prime X star. So after you get a sample from X star from Qx, you plug Qx star into this equation and get a probability which is less than 1, less equal to 1. Because we will pick a k to make sure k Qx star is always bigger than pi prime X star. So in the second step, pretty much like make a binary decision. You are drawing a Bernoulli sample with this probability. If the Bernoulli sample is 1, you are going to accept X star. If it is 0, you are going to reject it. So clear with these two steps, very simple. Okay. Pi prime is known. Pi prime is a function you defined. For example, you design a Markov random field. You can write down pi prime x, right? This is a potential function. And what you don't know is z, because z is sum over all the configurations of x over the pi prime x. But pi prime x is easy to know. So you can find its maximum value, and Qx is also known. You can decide the k.
So what is the difference between pi prime and Qx?
Pi prime and Qx. Pi prime is a potential function. Do you remember the potential function in Markov random field? For example, we have a very simple graphic model. We can define a pi prime x. X here is equals to x1, x2, x3. This is x1, x2, x3. So pi prime x can be defined as the pairwise potential can be defined exp phi x1, x2 plus phi x2, x3. Okay. This is the binary potential here, x3. Plus the unary potential, like x1, x2. This is an example of the potential function, right? The phi and the size are functions you defined.
So here also we are making an assumption that our overall model will be defined by this potential function.
So it's like this. Given a graphic model, you define this potential function. And given this potential function, you get into this distribution. But this distribution is very hard to evaluate because there is a partition function z here. But this is very simple to evaluate and analyze. Now the goal is to draw samples from this pi x. So about the pi x, what you know is pi prime x. And here, what we are doing is how can we draw samples from this distribution. And the strategy is to use another distribution qx to help us draw samples from the target distribution. There is no relationship between qx and pi prime x. Qx, in principle, can be any distribution which is simple to draw samples from. Okay. So the procedure is very simple. And any questions about the two-step procedure? You keep repeating these two steps to draw as many samples you want. So why this procedure works? In the sense that if we draw samples in this way, how can we guarantee that the samples is from the target distribution pi x? So here is a simple proof. Okay, let's say we draw sample x star from these two procedure. Now we compute its probability, x star. It is proportional to qx star, right? Because it is drawn from qx. And multiplies by the probability of acceptance, pi prime x star k q x star. The probability of x star is proportional to the product of these two quantities, because we first draw x star from Q, and in the second step we use this probability to decide whether we accept it or not. So to turn this proportional into equality, we add a normalizer, px star equals to q x star pi prime x star kq x star. The normalizer would be the sum or integration of all the possible values of this and oh, sorry, it should be x here because it is dx. So what we are doing here is we're trying to turn this proportional into equality. It's very simple. You just divide this unnormalized quantity with all the with it's like a partition function to ensure that the integration of px star is equal to 1. And so given this equation, we can cancel. There is a qx here and a qx in the denominator. So we can cancel these two qx cancels. And the k can also be cancelled. So we get pi prime x star integration of pi prime x dx. This is exactly the definition of the original distribution, right? Pi prime x star, pi prime, and this part is a partition function z. So that is to say px star equals to pi x. Any questions about the derivation? So if you are okay with this, we proved that Px star is exactly the same as the target distribution Px, and the Px star is from this two steps procedure. So that is to say, this two-step procedure will give you the samples of Px. Oh, that is here. So this is a probability, right? And in the second step, we are going to make a binary decision whether accept it or not. So how do you draw a sample from a Bernoulli distribution? You draw a sample like mu from a uniform distribution from 0 to 1, right? And you compare mu with this quantity. If mu is less than this quantity, you accept this sample, otherwise reject it. Right. So here, this is simply a practical way. How do you sample from a Bernoulli distribution? So this is the rejection sampling. Let's summarize the two steps. First, you define a simpler distribution Qx and draw a sample from it. And in the second step, you compute this accept probability and use this probability to make a decision whether you accept X star or not. It's very simple, but there is a problem is, let's take an example. So if my target distribution is like this is the Px, and you choose a distribution Q like this. It is a Gaussian Qx. So in this case, you are going to, because for the Gaussian distribution, the density is the highest density is here. So you are going to sample a lot of samples in this region, corresponding to the highest density of Gaussian distribution. However, the actual density of the target distribution Px in this region is very low. So remember the accept rate pi prime x over qx. So this quantity here is very large, and this quantity here is very small. So if you do the division, this accept probability will be very small. And with high probability, you will reject a lot of examples here, simply because this quantity here is very small. So in this case, what you are doing is you generate a lot of samples, but reject most of them. This is a big waste of efforts, because in a lot of cases, get a sample from a distribution is non-trivial. So this is the drawback of rejection sampling. You take a lot of efforts to generate a lot of examples, but reject most of them. Any questions about rejection sampling?
The rejection rate is smaller than the one that you rejected.
You can think of this like a parameter in Bernoulli distribution. You can think of this quantity as mu, and so Px equals to 1 in Bernoulli distribution is mu. So if mu is small, x equals the probability x equal to 1 is very small, and x equal to 1 is what you accept this sample. So that is to say, if mu is small, you are going to reject this sample with high probability. Any other questions? So let's get to the second sampling methods. We know that the drawback of rejection sampling is to waste a lot of samples, because it is highly possible that you reject most samples. Important sampling come up with this idea. I'm not going to reject any of them. All the samples drawn from Q will be accepted. So important sampling is kind of an improvement or remedy of the rejection sampling. Important sampling is like this. Still, we consider a distribution Px. It is a ratio between the potential function P prime x and A. I changed the notation a little bit. In the rejection sampling here, it is pi prime x over z pi x. They are basically the same, just the notation is different. So we want to still generate samples from Px. And we are going to use the samples from Px to compute the expectation of our function defined over x. This means the expectation of fx defined over the probability Px. This is like fx Px dx, which is the expectation of fx. We want to compute this guy. So let's do this. The expectation of fx defined as fx Px dx. We divide our qx here and multiply our qx here. It doesn't change anything, right? Divide something and multiply something. And the definition of Px is like this. So we can, because A is the partition function, which does not depend on x. So we can take it out of the integration. Fx P prime x Qx and Qx dx. We simply plug in the definition of Px into here and take A out of the integration, because A doesn't depends on x. We define P prime x over Qx as we use gamma x Rx to denote this quantity, and plug it in